you. Today I am going to discuss about the basics of transformer. So transformer is a static device which is used to transfer the electrical energy from one voltage level to another voltage level. So basically it is called as a static device because there is no rotating part in the transformer, right? So here we can see in the definition that the transformer can be either a step up or a step down. Means if we need to have a step up the voltage, if we need to increase the voltage level, we can use a step up transformer. Or if we want to get a low voltage level, then we can use a step down transformer, right? So transformer is basically a static device because there is no rotating part in the transformer. That's why it is called as a static device, and it is used to transform the electrical energy from one voltage level to another voltage level. This is the very basic of transformer. Now the working principle of transformer we'll discuss. The transformer works upon the principle of mutual induction, right? Here we can see that what is the need of transformer. This is the power system diagram where this is a generating station. We know that the generation is done at the low voltage level, transmission at high voltage level, and the distribution at again low voltage level. So while the generation, there will be a low voltage level, then for getting the electrical energy to being transmitted through the transmission line, we need to have a transformer between the generating station and transmitting station. So this transformer must be a step up transformer which is used to increase the voltage level of the electrical energy to be transferred. Now after transmitted this electrical energy, we need to distribute it through the distribution end, and we know that the distribution is at the low voltage level, so we need to have a transformer between the transmitting end and distribution end. So this transformer must be a step down transformer to get the low voltage level of the electrical energy to be distributed, right? So now we will come to the basic principle of operation of transformer. So as I have said that the transformer works on the principle of mutual induction. This is the circuit diagram of transformer. So here this is a core of transformer, and now I'll discuss what is the mutual induction. So mutual induction is actually nothing but when the two coils are placed very near to each other, like we'll discuss in this circuit diagram. When the two coils are placed very near to each other and we provide the electricity or electrical energy to the first coil like this, so the current will start flowing through this coil, and because of this current there will be a magnetic field generated around this coil and the flux start flowing through this path. There is a change in the linking flux, right? Then an EMF will be generated according to the Faraday's laws of induction. An EMF will be generated in this secondary winding like E2, and because of that EMF, if we provide a closed path through this EMF across the load, then we will be having a current flowing through this winding also. So this is the mutual induction, that in spite of not connected this secondary winding to any electrical source, there is no electrical connection with this secondary winding, but the current will start flowing through this winding because of only induction. So this is called as mutual induction, and we know that there is an AC supply. So AC supply is actually the sinusoidal AC. So the flux which is being generated through this winding, it is also alternating in nature. So because of the alternating in nature, there will be d phi by dt, the rate of change of flux. So the EMF generated in this winding E2 will be proportional to d phi by dt, that is the rate of change of flux. So this is the basic principle of transformer that we are having over here. The mutual inductions. This is a core of the transformer. This is a core made up of iron material, made up of magnetic material like iron or aluminium, right? And this is the winding. This is called as primary winding, and this is called as secondary winding, right? And this is the winding. This is called as primary winding, and this is called as secondary winding, right? the primary winding is connected to the supply, single phase AC supply, and the secondary winding is connected to the load. So this is called a secondary winding. Let us consider that there are N1 number of turns in the primary winding and N2 is the number of turns in the secondary winding, and the single phase supply is connected through this primary winding. So a current start flowing through this primary winding, because of which an MMF will be generated. Suppose I1 current is flowing through this, so N1 I1 will be current generated through this winding. Because of that, a flux will be start flowing through this path of the core, and it will link to this secondary winding also. When there is a flux linkage with this winding, an EMF E2 will be generated in this winding, and because of that EMF, a current I2 will start flowing through this load. So this is the basic principle of operation of transformer, how it works on the principle of mutual induction. So this load current I2, suppose this is the load current I2, the voltage is V2 across this load. Suppose the V1 is the supply voltage, E1 is the EMF generated in the primary winding, N1 is the number of turn in the primary winding, and N2 is the number of turn in the secondary winding. Right? So this is the basic principle of operation of a transformer. Next, this is the EMF generated in the primary winding. This is proportional to d phi by dt or minus N1 d phi by dt, where N1 is the number of turn in primary winding. E2 is the mutually induced EMF, and this is equals to minus N2 d phi by dt. N2 is the number of turn in the secondary winding. Negative sign is because of the Lenz law. According to Lenz law, it will oppose the reason because of which it is generated. So next we come to the types of transformer. Basically there are three types of transformers: shell type, core type, and berry type. So this is the first type of transformer, that is shell type of transformer. There are three limbs, and the primary and secondary winding is provided on the central limb of the transformer. So the primary winding is wound over the central limb of transformer. Then a paper insulating material is wound over the primary winding, and then over it the secondary winding is wounded over the central limb of transformer. So this is called as shell type transformer. Next, in core type transformer, there is a core. This horizontal part is called as yoke, and this is a limb, and this is also another limb. So this is called as primary limb, where the primary winding is wound in the transformer and the supply is connected over here. This is the secondary winding. This is the secondary winding is wound over the secondary limb, and the load is connected over here. So this type of transformer is called as core type transformer. Next we come to berry type transformer. In berry type transformer, the core construction is like spokes of the wheel. This type. Here the high voltage winding and low voltage winding are wounded over here, and the whole assembly is immersed in the oil, in the tank filled with the oil. Right? So now according to their working, there are step up transformer, step down transformer, and isolation transformer. So first come to the step up transformer. What is a step up transformer? Suppose if you are having N1 number of turns in the primary winding, N2 is the number of turns in the secondary winding. So if we want to increase the voltage level, we need to have step up transformer. So step up transformer is a transformer which is having more number of turns in the secondary winding, means N2 will be greater than N1. So if N2 is greater than N1, then the transformation ratio, that is called as K, K is N1 upon N2. So these type of transformers generally used as I have already discussed, that between the generating station and transmitting station there will be a step up transformer. Right? So these transformers are having more number of turns in the secondary winding as compared to the primary winding. So N1 upon N2 is K, and K will be less than 1. Right? We know that if N2 is greater than N1, then this ratio will be less than 1. So the term ratio K will be less than 1 for step up transformer. Same for step down transformer. If we need to make the voltage level down, if we want to reduce the voltage level, then what we will need to do, we should reduce the number of turns in the secondary winding. So step down transformer R1, where N2, the number of turns in the secondary winding, are less than the number of turns in the primary winding. So K, that is the turn ratio, N1 upon N2 will be greater than 1 for step down transformer. So these transformers are used basically where we need to decrease the voltage level of our power supply. The third type of transformer is isolation transformers. These are the transformer where the N1, number of turns in the primary winding, and number of turns in the secondary windings are same. So what will be the need of transformer when the number of turns in primary and secondary winding are same? It means that the primary voltage V1 and secondary voltage V2 will be same. So these transformers are used to isolate two electrical circuits. Suppose we are having one electrical circuit and another electrical circuit, and we don't want any electrical connection between them. So we need to connect a transformer between them, so that with the equal number of turns, so that V1 is equals to V2 and the turn ratio will be 1, and there will be a isolation between the two electrical circuit, because in transformer between primary and secondary winding there is no electrical connection. They are electrically insulated with each other and magnetically coupled with each other. So next we'll come to rating of transformer. The rating of transformer is given as kVA, kilovolt ampere. So if we have the rating of transformer, suppose 100 kVA transformer is there, we can get the primary current and secondary current by this rating of transformer. Like if we have kVA rating and voltage rating of the transformer, because transformer rating is always given in kVA rating plus primary voltage and secondary voltage, right? Suppose for example we are given a 200 kVA 20/10 kilovolt transformer. Then find out the primary and secondary current. So primary current I1 will be kVA rating upon V1 into 1000, because this is the kVA rating, we need to change it in volt ampere, and the secondary current I2 will be kVA rating upon V2 into 1000, right? So kVA rating is V1 I1. So we need to learn that V1 I1 is always equal to V2 I2 in the case of transformer. Means the primary kVA rating is equal to the secondary kVA rating of the transformer. So in case of transformer, the volt ampere rating is not being changed. It is same as for primary as for secondary. Now ideal transformer. So ideal transformer is a transformer where there is no losses, right? So copper losses in the windings are 0, iron losses in the core of the transformer are 0, and no magnetic leakage. So there is a transformer which is having no losses or very less losses are there, and approximately having 100% efficiency, which is called as ideal transformer. So this is the circuit of an ideal transformer. Here is no winding resistance or reactance. Here on the secondary also there is no winding resistance or reactance. So this is called as ideal transformer. So we can draw the phasor diagram of ideal transformer. This is the flux phi m. Then E1, E2 and V2, since E1 and E2 are lagging behind the flux phi by an angle 90 degrees. So E1 and E2 will be drawn over here by lagging an angle 90 degree. Since E2 is equals to V2, so V2 will be drawn on the same axis as E2, and V1 is equals to minus E1. So V1 will be drawn in opposite direction of E1. So this is a V1, right? So this is a phasor diagram of an ideal transformer, right? This is the primary current, because this is a primary current at no load condition, at no load, because yes, on no load. This is on no load condition. This is the transformer. So when there is no load connected in the transformer, so this I2 current will be 0, secondary current will be 0, so only primary current will be there, and this primary current is called as exciting current I0. So this exciting current has two components: magnetizing component of current and active component of current. So magnetizing component current is called as I mu or Im, and active component of current is denoted by IE. So there are two components of current. So phasor diagram of an ideal transformer at no load. is like this. This is not for ideal transformer, sorry, this is for actual transformer. Here this is the phi m, the flux flowing through the core. E1, E2 and V2 are lagging by 90 degree. V1 is minus E1, so V1 is drawn over here in the phasor position of E1. Then this is the primary current which is lagging behind the primary voltage by an angle phi naught, and I naught is having two components, that is I mu or Im and IE. So this IE is I naught cos phi naught and this I mu or Im is I naught sin phi naught. So there are two components of I naught. So I naught can be equal to under root of Im square plus IE square. But in ideal case, I naught is equals to Im only, because there is no IE, no winding resistance. Winding resistance is 0, so IE will be 0. So in the case of ideal transformer, this phasor diagram becomes as this one, because it will become a pure inductive. Winding resistance is 0 in case of ideal transformer, so the current, some supply current, will lag behind the voltage by exactly 90 degree, right? So this is the phasor diagram of transformer, ideal transformer at no load, and this is the phasor diagram of ideal transformer, actual transformer on no load condition. So in the next lecture we will discuss how transformer on no load and transformer on load condition can be equalized, and the equivalent circuit of the transformer we will discuss in the next lecture. Thank you.